Given a destination mile called target, plus position and speed arrays for every car on a one-lane road. Cars cannot pass each other, a faster car slows down when it catches the car ahead. Count how many separate fleets reach the destination. Example 1. Target is 12. The cars at miles 10 and 8 both need 1 hour to reach 12, so they arrive together as one fleet. The car at mile 0 never catches anyone else, so it is a fleet by itself. The car at mile 3 catches the slower car at mile 5 and they travel together, forming a third fleet. The answer is 3. Example 2. Target is 10 with a single car at mile 3 and speed 3. It reaches the destination alone, so there is one fleet. We have a group of cars driving down a strict single-lane highway toward a finish line. Each car starts at a different position and travels at a different constant speed. The catch? It is physically impossible to pass the car ahead of you. If a faster car catches up to a slower car, it is forced to hit the brakes and match the slower car's pace, merging into a single unit called a car fleet. Our goal is to determine exactly how many unique fleets cross the finish line. Trying to simulate this second by second by tracking exact positions on the road gets incredibly messy. To simplify our mental model, let's shift our perspective from speed to time. We calculate exactly how long it would take each car to reach the finish line if it had the entire highway completely to itself. Suddenly, raw speeds turn into clean, predictable arrival times. To figure out who collides into whom, we have to evaluate the cars starting from the front of the pack back to the rear. The car closest to the finish line is the absolute leader. It dictates its own destiny because there is no one in front of it to block it. By sorting our cars based on their starting positions in descending order, we can systematically process the highway from the front leader to the trailing tail. Now we march backward through our sorted line. Car A sets our initial pace, taking 1 hour to finish. Next up is car B. It also calculates out to 1 hour, meaning it intercepts car A exactly at the finish line. Because it hits that barrier, it merges cleanly into car A's fleet. Finally, we look at trailing car C. It requires a massive 12 hours to finish. Since 12 hours is greater than the 1 hour fleet ahead of it, it can never catch up. It is fundamentally stranded in its own independent fleet. By using a stack to track our time horizons from front to back, the logic becomes seamless. Any car that takes less time than the fleet leader ahead of it simply vanishes into that fleet. Any car that takes longer becomes the leader of a brand new fleet. The final size of our stack tells us the exact number of unique car fleets that will cross the finish line. For our highway, the answer is 2. We kick off our code by packing our separate position and speed arrays into a single, cohesive roadmap. We pair each car's starting position with its speed and sort the entire list in descending order based on proximity to the target. This ensures our code processes the highway exactly like we did in our intuition, starting from the front leader and working our way backward. Now, we initialize our core data structure, a standard stack. Because of our highway logic, this container will naturally only hold arrival times that are strictly increasing as we look deeper into the stack. In computer science, this pattern is called a monotonic stack. We will use it to hold the time horizons of our active fleet leaders. We enter our loop to process each vehicle. For every car, we instantly calculate its independent arrival time by subtracting its current position from the target distance, and dividing that remaining gap by its speed. In languages like Java, cast a double before dividing so the arrival time stays fractional. We store this value as our current _time. With our arrival time calculated, we check our stack's current leader. If the stack is empty, this car is the ultimate front runner, so we push its time straight in. But for subsequent cars, we look at the top of the stack. If our current car's arrival time is less than or equal to the leader ahead of it, it means this car will collide with the fleet before the finish line. Because it gets absorbed into the existing fleet, we do absolutely nothing and let it discard. If a trailing car calculates an arrival time that is greater than the fleet leader ahead of it, the collision condition fails. This car is simply too slow to ever catch up. It anchors a brand new independent fleet, so we append its time directly onto our monotonic stack to act as the new pacesetter for any vehicles behind it. Once the loop finishes scanning every vehicle on the highway, our monotonic stack holds exactly one unique arrival time per fleet. The final size of our stack is our answer. We return the length of the stack, and our fleet tracking system is complete. Let n be the number of cars. Time is order n log n, sorting by position dominates, then we scan each car once with constant time stack pushes and skips. Space is order n for the sorted car list and the monotonic stack of arrival times. Pseudocode for car fleet, zip position and speed, sort by position from nearest to farthest from the target, then walk the list. Compute each arrival time with floating point division. If the car would catch the fleet ahead, skip it, otherwise append its time to the stack. Return the stack length.